It's not working, but I'll deal with that later. Uh, I'm really excited for another session of the Denver Data Drivers. Thanks for joining, everybody. As always, remember to look up and down the list of participants on the side. This is really kind of hopefully a group of people that certainly we think are sort of thinking about digital processes and how the workflows in oil and gas are changing. And so there's a lot of you guys are the leaders that are making some big changes in the industry. And I think we're going to get to know each other a lot more as time goes on. Sean Kristjansson is speaking today on Bayesian mixed models, and especially in comparison to some of the sort of more standard, more linear processes that we tend to do with our models and the way we build inversions and build forecasts in oil and gas. So this is going to be a great talk. There's some really interesting people over at Ovintiv who really paid a lot of attention to some of the statistical concepts and how to really make applied decision tools. So I'm really excited about this. I want to make a note about next week. We have Santiago Cuervo talking about his GitHub repository, which really ties into some of the cash flow and value impacts of operating wells and managing wells. So I'm really excited to have him walk through some of what he's built, kind of an open source field management tool over there. But that's next week. This week, we have a really great talk from Sean. We'll have some Q&A. I am sure you'll have some questions at the end of this, which I'm excited for, but really don't have a whole lot more to offer. So I'm going to let Sean kick it off.
Yeah, great. Thanks, Kurt. Thanks, Mindy. I really appreciate you guys for, leading this group, getting us all together, and I really appreciate the opportunity to show this work. I'm pretty excited about it. It's been a really kind of big project for us. And it's a team effort, right? So, I just wanted to take a second to acknowledge the team, David Bonner, Natalie Sordow, Cameron Cross, as well as Ryan and Tina. They've all kind of throughout the life cycle of this project, they've all made contributions to it. So, without their help and support, I certainly wouldn't be sitting here in front of you today. So just a quick note on where I sit inside of Ovintiv. So I sit inside the data science team, which is part of our central information management group, part of IT. So, I'm not working out there kind of in the asset teams. I'm sitting central. So, when we build something, when we put models together and wrap it up into some kind of an application, we're always thinking, what can, we want it to be, cross-asset and portable, right? So anyways, that's kind of where I sit within the company. Yeah, so Bayesian mixed effect regression models and workflow. So it's kind of a mouthful, right? And there's actually quite a few moving parts to this. And the major moving parts, like there's this Bayesian piece, right? There's this mixed effect regression piece, and then the entire workflow piece. And I could easily spend more than an hour talking about each one of these different parts. For today, though, I hope I'm not disappointing the people who are particularly here for Bayes. I'm not going to talk that much about the Bayesian part. And I'm going to focus more on the mixed effect regression part. So hopefully maybe Kurt and Mindy will have me back sometime and we can go like deep dive into the Bayesian part. But I'm going to focus on the mixed effect regression part. And the reason I'm doing that is, the mixed effect regression part is really what's driving the gains that we're seeing in our models, predictive and prescriptive performance in the well design optimization space. So, at least at this point, it's not so much the Bayesian part that's making a difference as it is the mixed effect part. And I really want to highlight that fact today. So for those of you who really haven't heard much about mixed effects regression models, they're used heavily in the not so much the machine learning world, but more in the kind of the statistical modeling side. There, you'll sometimes see these things called, multi-level regression models, hierarchical linear models, random coefficient or random effects regression models. So depending on who you're talking to, you're going to hear them called by different things. So, if you're not familiar with these things, what I'm hoping for today, at least by the end of the talk, hoping you'll at least have a feel for what mixed effect regression models are. At the core of what they are is just a very clever extension to classic multiple linear regression. So just want to make that point clear today, and I hope that's okay with everyone. I hope I'm not disappointing anybody who wanted to hear about the Bayesian side of this. But like I said, I'd be happy to talk about that at another point. All right, so here is what I'm going to talk about today. First, I'm going to walk you through, kind of the business objective driving this work, right? So, we're looking for a prescriptive model that our engineers can use as a tool to help optimize our new wells. I'll also walk through the design requirements, not only for the model, but for our app. So I'll talk a little bit about that. I'm going to dive into sampling bias and how it creates problems for machine learning algorithms in general, but also how it messes with classic multiple linear regression in particular. So why I'm focusing on MLR is, a lot of people use it, a lot of people know it. Internally, it's still used here a lot at Ovintiv for work, building models and using subsurface data, and also other business use applications. I'm going to focus in and go into a fair amount of detail about one particular form of sampling bias. So this form occurs or when our data live or tend to exist in, some might say like occupations, some might say subsamples, some might say subpopulations. More generally, they live in these group or clustered data structures. And I'll actually show some graphics here in a couple minutes to explain exactly what I mean by a clustered data structure. So I'll go through that. Then next, I'll walk through a case study in our Montney asset. So for those of you who aren't familiar with the Montney, here it is on a map. And you can see that this play straddles the western Alberta, eastern BC borders, kind of in the northern half of the provinces. When I walk through that case study, I'll try and describe a little bit more about what the mixed model is and how it's different from classic MLR. So here's the fair warning. I'm going to get kind of mathy and technical through that part of the talk, but I'm hoping it'll be worth it. That's part of why some people are here. And I hope you'll see that it's worth it when I talk about the models or the mixed models predictive and prescriptive performance. So along the way, I'm also going to weave in some discussion about how we've overcome roadblocks and hurdles kind of throughout the life cycle of this project. We didn't start this yesterday. It was actually a side of my desk project that I had ready to go 4 years ago, but it's taken a long time to kind of get this out the door. So talk a little bit about, what's got in our way and how we've overcome those roadblocks throughout the rollout. And the end, I'll leave some time for questions and discussions or a discussion. So business objective. So the objective is we want to implement a workflow to train, test, and deploy a scalable model that our teams can use and interact with to help them engineer and optimize our new wells. So we're looking for a prescriptive model. I mentioned that a couple times. So, and what I mean by that is, we're not really interested in making predictions per se. I mean, we are, but We're really more interested in knowing how and why we arrived at those predictions. So the idea is if we know what's driving the accuracy of our predictions, we'll know what's driving our well performance, and we'll have a model that people can feel comfortable with using it as an optimization tool. So attributes are what we call attributes internally. Some people call these features, some people call them in the statistics world independent variables. Those need to be those things that we know are primary drivers of well production. We know better geology, you get better wells, well spacing, etc. These are all important things driving the performance of our wells. So we're requiring at least one attribute from each of these three categories to be used in our model training. So our attribute weights are regression slopes. It's another word for them. These need to make physical sense and really align with subject matter expert knowledge. I'll talk, there's more on this to come in a minute, but like as just a simple example to kind of give you an idea of what I'm talking about here, you know, if our model is telling us that the relationship between, say, lateral length and production isn't linear, and there's probably something wrong with the model. We need to go back into it. We need to debug it. We need to figure out what's going on, or maybe just go back to the drawing board and start over. That's a real important piece of this. We also want our model to account for sampling bias, these clustered data structures that I mentioned. And I'll go into more detail on that in a moment as well. So the last requirement is that our app is scalable. The models inside our app can be portable across our assets, and that will, you know, all our asset teams can be find easy, essentially easy to use. All right, so let me talk a little bit more about this one requirement. Our attribute weights need to make physical sense, and they need to align with our subject matter expert knowledge. So what our reservoir engineers and geologists and geophysicists are discovering, at least up in the Montney, is that not all areas of the Montney are created equal. So as an example, what they're seeing is that the same completion intensity equals different uplifts in production depending on where in the Montney you're at. So you can see a little bit of what I'm talking about on these graphs. So what I've got plotted here is the percent production uplift on the Y as a function of intensity plotted on the X and effort plotted, or intensity plotted on the X, sorry, in two different areas. But what you can see is that increasing the clusters per thousand, or increasing clusters or increasing intensity in area 1, that uplift rolls over at a different point in area 1 than it does in area 2. So it actually rolls over earlier at a lower intensity in area 1 compared to area 2. So what this told our subject matter experts is that, you know, a one-size-fits-all type of modeling algorithm won't do. Our SMEs were asking for a type of model that allows for different completion uplifts with different rollover points in different areas of our land base. So that's what we tried to build. So another major design requirement is that our modeling algorithm needs to be robust to sampling bias. All right, so I'm going to spend a fair amount of time unpacking this and what I mean by this. So, you know, most out-of-the-box machine learning algorithms assume data are randomly, independently, and representatively sampled. So this just isn't the case in subsurface data sets. So they're sparse, they're non-random, and they're spatially dependent. So there's a really good paper that I just want to throw out to everybody. Michael Perch and the UT Austin group actually have a great paper on spatial sampling bias. It's definitely worth a read. If you don't have time to read it, though, the key takeaway is that if you're using machine learning, some type of machine learning algorithm on subsurface data, use an algorithm that removes or at least mitigates the effects of sampling, spatial sampling bias. And they do a really nice job of explaining, how they pre-process their data to what they call spatially decluster it before they run it through a machine learning algorithm. Here, we like to take a slightly different approach than the UT Austin group. So we like to think about spatial sampling bias more as a clustered or subgrouped data structure problem. Let me dive into this to really show you what I mean here. So in our Montney asset, so we've got these subgroups of wells that kind of live or come from these different geologic areas in our land base. So you can see some of these groupings start to pop out when I plot the well locations on a lat-long grid. Now we can say these groups or these subgroups are actually biased samples because they're sparse samples and they don't represent the population distribution of wells in the Montney. So another way of saying this is that these wells from these different subgroups are not alike. They're actually quite different from one another. You can actually see these differences pretty easily. So what I'm showing here is the log 2-year cum distribution for all the wells in our sample. Now here's the distributions for wells in 4 of our geologic subgroups or subregions. You can see that the mean of these distributions, or even the median, are actually quite different from one another. And these distributions have like these different, essentially different shapes. None of these subgroup distributions look exactly like this one either. So we can say that these are actually sparse, non-representative samples. So we can see that sparseness and non-representativeness again when we look at completions. So here's intensity and our subgroup distributions for intensity. And again, you can see they have different means. This one's even bimodal a little bit. They have different shapes. You see the same thing again for clusters per thousand or clusters per foot. We see the same thing again when we look at well geometry. So here's well spacing. The subgroup distributions are different from one another, and they're different from the overall sample, as well as lateral length. Now I could keep showing you like more attributes or more features, and we continue to see the same thing again and again and again. And what we'd see is that the well subgroups are structurally different from one another, and none of the subgroups really represent the population of Montney wells. So now this turns out to be really important, and here's why. So we know that this form of sampling bias causes problems for classic multiple linear regression. So, this has been, known for actually 40 years, and there's actually a pretty robust statistics literature on this. But the problem when applying MLR to these clustered data structured samples is that that form of sampling bias, it actually creeps in and messes up the MLR's attribute weights. So the attribute weights or the regression slopes, if you were to apply MLR to these data, would be too small Some would be too large, or they might even be physically unrealistic. So what that means is if we're using an MLR model, using that algorithm to train a model for a prescriptive tool for well optimization, the tool is going to overestimate or underestimate the effects of completions and the effects of other attributes like well spacing, lateral lengths, geology. All right, so to summarize, we need a model that has met all our other design requirements that I mentioned earlier, but also adjusts the attribute weights for these clustered data structures. So the technical term of the modeling algorithm that we're using to do that is exactly what's in the title of the talk here. It's that mixed effect regression model. But that mixed effect regression model is just the engine that lives inside our application that we are like building into a complete workflow. So that app we've affectionately named internally as B3PO. So you might hear me use the term B3PO and mixed models interchangeably going forward. But I'm just referring to the mixed effects regression model. But the cool part of that is I'm bringing in Star Wars here. So B3PO is just an acronym for our Bayesian WellPad and WellPad performance and prediction optimizer. So, here's B3PO, and we've got this little guy over here, R2V2. We use R2V2 to kind of visualize the model parameters, the model predictions, the things that are kind of going on in our mixed effect model as when we're done, or when we're training it and we're interpreting the results. That's where we're using R2V2. Natalie Swartout and now Cameron are building that out for us right now. So anyways, that's where we get that name from. All right. So that was a lot. I kind of went through it really quickly. Before I kind of walk through the, where we apply B3PO or a mixed effect model in the Montney, is there any questions or things you wanted me to clarify? If there's not, that's fine too. We can wait till the end. Is there anything from anybody? Okay, I'll take the silence as a thumbs up. We're good to move forward.
Is the main point that you're kind of highlighting here that when we think of spatial clustering, that no matter how you draw you create any kind of AOIs, that those AOIs have sampling biases in them, and so when you start bringing them together, you have biased sets.
Yes, that's exactly right. And yeah, that's exactly right. So, there's a bunch of ways that we can determine, what areas of interest that we are, that just kind of slice and dice our data up into all these different areas of interest, right? There's different ways to do that. We did it a bunch of ways. We kind of landed on like this balance between, it was really driven by our subject matter experts. David Bonner was the guy who like came up with all these different subgroup structures in our data that we used in our final model. But we tested out a bunch, and everybody kind of needed to be happy with it. And we also, and they just needed to make sense, right? But no matter which way you slice and dice, there's always going to be some bias that creeps in. And I've seen that in data set after data set and, land base after land base. So yeah.
Got it.
Okay. Is that it for now? We're good? Should we just move on? Let's do that. Okay. So here's the data that we're using. So in our Montney land base, we have like 520 wells, not a huge sample size, right? We're actually doing like a 80-20 test train split. What we're trying to optimize on is two-year Q, like I said. And we're using these these 8 different attributes, 3 geologic attributes, couple spacing, and then, we have effort and intensity, lateral length. Also to help mitigate the effects of sampling bias and these 9 areas that we've identified, like I just said. These are essentially geologically consistent areas in our land base that our subject matter experts identified. And what I'll show you in a minute is these 9 areas actually become part of the mixed model itself. I'll show you that. First, though, let's talk about what the mixed effects regression model actually is. So like I said earlier, you can really think about it as an extension of classic MLR. So here's one way to represent multiple linear regression as an equation. Again, y is what we're trying to predict. That's two-year Q. Our attributes are in blue, and our attribute weights are these betas in black. So in MLR, we calculate just one attribute or one weight for each attribute. In B3PO, we're essentially solving the same equation, but here's the difference. In B3PO, we actually have 9 weights for some of our attributes. So, 9 weights for some of our attributes and 1 weight for some of our others. And I'll show you that in a minute. So for those of you who don't like equations but would rather see numbers, so here's the weights from our MLR. So we have 1 intercept, and then we have 1 weight for each of our other attributes. In B3PO, we have 9 different intercepts, 1 for each of our geologic areas. We also have 9 weights for propant, 9 weights for cluster spacing, and just 1 weight for other attributes. So, as I've presented this to people in the past, or internally, one of the concerns I get is that, adding this additional complexity, is your model overfitting the data, right? So it's a great question. And, how we address that is, we examine predictive accuracy on test data, right? So why do we do that? Well, we know the predictive accuracy for an overfit model on test data is going to be very poor. It's going to suck. So for MLR, our MLR version of this, I've gone ahead and calculated some accuracy metrics. So what I've got plotted here is the actual production on the Y, predicted production on the X. I've gone ahead and calculated our square as well as our root mean square error. So I went ahead and did it for B3PO using the identical attributes, but we're just allowing for some flexibility in those regression coefficients. And you can see that our accuracy, our square increases by about 21%. You can see that our RMSE decreases by about 13%. So, when I show this to our asset team or asset teams, that really gives us confidence that our mixed model is not overfitting the data. Otherwise, we just won't get buy-in and people won't use it. So it looks like we're onto something good. Again, one of the other things that we've had to do is, explain, how we're getting the improvement in predictive performance. And like I said at the beginning, we're not all that interested in making better predictions, more accurate predictions, as we are in, where interest really lies in, how and why we're getting to those better predictions. So what's going on under the hood, I'll try and show you that in another way. So what I'm showing here is the percent production uplift on the y-axis as a function of increasing intensity and increasing effort on the x. Now you can see that B3PO is actually calculating different completions uplifts in different areas. So in this pink area, there's less uplift in production that we're going to get by increasing clusters per thousand. In the green area, we're going to get more uplift. So this is the main reason why B3PO is better predictive performance. It actually is calculating area-specific uplifts or area-specific attribute weights. So it's not a one-size-fits-all model. It acknowledges, what our REs and our GEOs have seen is that, completions are not working the same in every area of the Montney. So another hurdle that we've bumped into during the rollout is we keep getting the question is, why do I need this mixed model thing when I could just train 9 separate MLRs, one for each of our 9 areas? This is a really good question. And the short answer is that B3PO, or our mixed model, actually has another key part that makes it different from classic MLR. So I'm gonna do my best to make this difference really clear and to spend a little bit of time unpacking this. So for those of you who don't like equations, I'm going to show you more equations. So MLR is part of the general linear model family. And here it is in matrix notation. And again, what we're predicting is y, it's 2 your cube. Our attribute weight, our attribute data that we're using to train our model live here in this matrix X, and our attribute weights live in this matrix B. Our residuals or our model errors live in this vector epsilon. So like I said before, MLR calculates one weight for each attribute. There's one intercept that lives in here, one weight for lateral length, for all our other attributes. So, because MLR calculates one weight for each attribute, we can say it's an average of all algorithm. We can also say its attribute weights are average of all weights. So the one thing I haven't mentioned about the mixed model or B3PO is it also calculates average of all weights, but it's not part of the general linear model family. It's part of the general linear mixed model family. You can see it has some of the identical terms as MLR does. But the difference here is it actually has these other 2 pieces. So for this part of the discussion, I'm going to just focus on prop per cluster. So I'm just going to focus on this prop per cluster, and I'm going to focus in on this uniqueness matrix. So like I said before, sorry, I got my presentation a little out of order here. So like I said before, B3PO also calculates average of all weights. And it's very similar to what we get in MLR, but here's the difference. So what I'm going to do to show the difference is plot B3PO's average of all weight for prop per cluster on a graph like so. And like I said, B3PO also calculates 9 weights for effort, one for each of our geologic areas. I'm just going to show these now on the graph to show their relationship with this average of all weight. So here's the weight for area 1, which is negative 0.099. For area 2, it's negative 0.061, and so on. So let me talk a little bit more about this, because this is the place where these weights for our nine different areas kind of live together. So you can think of this matrix kind of like as a correlation matrix. So this is where the weights from our 9 different areas are bonded together. It's where they talk to each other and they share information with each other through their correlations with each other. So this is actually really cool. So this uniqueness matrix acts like a constraining force on the area specific weights. It pulls them in towards the average of all, like so. So another way you can think about this matrix is that it kind of keeps them from straying outside of or being calculated outside of the bounds of our data space. What that means is, the mixed model, having this in this mixed model actually is preventing B3PO from calculating unrealistic weights that form physically unrealistic relationships with production. So I'm not sure that I made that really clear, but I'll try and just keep driving this home for another minute or two here. So, the next question we get is, why are some of these weights farther away from the average of all? And why are some of these weights closer to it? And that's because there's actually another force operating. We call that local data support or local evidence. So in some of our areas, our geologic areas, our subgroups, there's more local evidence. And that means that that weight in those areas is allowed to travel farther away from this average of all. And this, by the way, also is how B3PO mitigates the effects of sampling bias. So this matrix here acts as a regularizing force that kind of that balances local evidence with the average of all. So let me hammer this home one more time. So if we were trying to do the same thing using multiple linear regression, like I said earlier, is we would have to train separate MLRs, one for each area, or we would have to put in our matrix here an interaction, or what some people call a cross effects term. So if we were to do that, what would happen is our weights might look something like this. So most would start to spread out. In very poorly populated areas, some might switch signs and start going in the wrong direction. And in other areas, some might go completely outside of our data space and start moving over to that dark side. But with our mixed model over here, we have this matrix that brings kind of balance and stability to our modeling universe. So let me hammer this home just one more way. I hope I'm not going overboard here, but I'm just going to say it again in a different way. So, we're looking at a different plot now. So again, what I've actually got plotted here is I have I have effort plotted on the y, and it's actually the reciprocal of effort. I'm not going to go into too many details about why we did that, but as you move from left to right, the amount of propant per cluster is actually increasing. It's not decreasing. On the y-axis here is what we have. We have this adjusted, what we're calling adjusted production. So that's the residual after training a model. After training a model with all the attributes in it except for propant for cluster. So the black line is just the line of best fit through those data points. So it's really pretty close to what we would get if we're able to train a separate MLR model using just the data from this specific area. You can see that the slope of this line starts to move up in a positive direction. So what this is actually saying is that, if you were to use less propant, you're actually going to get more production, which we know is just not true and it's physically unrealistic. So the B3PO, this pink line, is the B3PO line of best fit. And you can see that it's still going in the proper direction. So it's telling us that using less propant is going to give us less production. So it's going in the correct direction. So I can just show this in other areas as well. So you can see the slopes of the black lines in area 3 and area 5 are positive. You can see this is especially kind of bad in area 5 here, where this, this one data point is really leveraging that line of best fit through our data and, making our slope move off into, into the completely wrong direction. You can also see that, in all our areas, the B3PO lines, which are the blues, as well as the purple and the orange, are all going in the correct direction. And they're all telling us that using less propant is going to give us less production. And that's because we're using that uniqueness matrix, again, as that constraining force. It's holding everything in check and regularizing these attribute weights in these different areas. Yeah, so that's kind of a really cool thing about this mixed effect model is it allows you some flexibility of training separate MLR models, but it's not a separate MLR model. They're all held together. So we think that's pretty cool. So, but before we, roll this out to our asset teams, they want to know that the model is working, not just at 2-year cum, but also at different points through the life cycle of the well. So, what they're asking is, do B3POs or the mixed models predictive and prescriptive performance that we see at one single time point actually extend to the other points in the different points in the well's life cycle. So what I'm showing here is the month by month R² for MLR from month 1 out to month 60, and I'm showing that in red. You can see the R² for 2 slightly different versions of our mixed model in blue and green. Likewise, I'm showing the RMSE for our B3PO models in blue and green as well compared to MLR in red. And this was kind of the last thing that we showed to our asset teams that kind of got them to buy in is, yeah, it seems like the step change in our predictive performance on test data seems to be persistent across time. And that was kind of the last thing we needed to do to convince them. And, hopefully it convinced you that, by using a modeling algorithm that has some more flexibility in it and doesn't really allow for, or isn't really a one-size-fits-all model, and kind of acknowledges what our subject matter experts saw in our data was that we had these different completions uplifts in these different areas. So kind of putting all that together in one kind of model and workflow and then rolling it out is kind of like what we've done here. And you know, these models are now, you know, moved into production, and our engineers are using them to design our new wells for our 2022 well, our program. So yeah, and that's kind of it. That's all I have. I know it was a lot. So I just want to say thank you and for letting me drone on there. Hopefully I didn't get too rambly, and we can sit and chat and talk about this. So open it for questions.
That was
Maybe-
awesome. Thank
Sorry,
you.
go ahead.
Yeah, I thought that was great. I have a question. So it seems like a main driver of this workflow is more in interpreting your input features. Do
Yeah.
you see rolling out to the end users like recursive feature elimination or shape leave out values or more advanced ways to kind of dig into that?
Yeah, like I think there are ways, you know, at this point, I believe kind of in our internal evolution here, you know, our engineers are, you know, our reservoir engineers and even our geologists, they spend a lot of time on building features, right? Engineering features like our well spacing variable or well spacing feature, for example. It's worked on by a lot of different people in a lot of different assets. And, you know, we could algorithmically decide on which one is the best. But that's a conversation that we have, you know, with the people who actually are building the features, right? So I think we might get there someday, if there's a desire for it. But right now we're, you know, really kind of relying on our subject matter experts to kind of tell us, you know, what to use. And they run a bunch of preliminary models and things to kind of arrive at what that is. So so we don't do it yet, but it's, yeah, we could totally do it at some point.
No, that makes a lot of sense. Then one more follow-up. Do you have any comments on sticking with a linear model compared to some non-linear models? Like when I think of the subsurface, like resistivity or geomechanics, it's hard to think of that as a linear feature.
Yeah.
So any comments on that would be awesome.
Yeah. So we actually, I'm actually kind of on the side working on, you know, how do we move this more into um, a non-linear space. So I'm actually building those currently. What I find personally is, you know, at least in the Bayesian world, like the optimizers, right? Or the MCMC algorithms and the priors, like they're pretty hard to like dial in and adjust and tune, right? So um, so the short answer to your question is yes, we are going to move in that direction. And I've started building those. The way we kind of got around that in this current workflow is, you know, all those attributes that we're putting into our model, we're actually doing some transformations on them in the background. So if there is a nonlinear relationship between one of our attributes and production, we actually do a transform on that attribute so that when we model it, we actually keep the model linear in its parameters, and then offload that nonlinear piece to the actual transforms on those attributes before we put them into the model. So we're kind of going both directions. the transforms path that we went down seem to resonate more with our teams, or the Motley team at this point.
Yeah, Sean, I can kind of comment on that a little bit further, and that, yeah, you're exactly
Hi,
right.
Cameron.
And hi, sorry, I'm Cameron. I'm one of his coworkers.
Yeah,
Yeah.
and Cameron's like doing some great work with, rolling these out into our other assets and building our app and everything too, and coding. So just want to shout out to Cameron there.
Yeah, the big key there was kind of at the end of what he said, is that we handle the nonlinearity in the transformation of the input variables themselves, and we really like that kind of focus currently, because even things like Shapley values, right? Like, it's really hard to even using Shapley values understand interactions, because it's just, you have to do all sorts of color by when plotting and all these things. So we like the idea of keeping the model simple. Like Sean said earlier, it's not about the final prediction. It's more about the interpreting of the effects. And so by controlling exactly how we engineer those variables, it really allows us to have a better understanding of the effects of them.
Yeah. Also too, at some point, like our, the senior managers kind of need to explain this stuff to VPs, and you keep the model simple and the relationships simple. It helps that, we find. I think our VPs might get there someday, but it's going to be a while.
Yeah, I had a question about on that front, but Paul Devine had a question about whether the weight coefficients were mappable, and then he had a second question which I don't fully understand, so it may be easier to read what he had. But that's an interesting point, though. Are those you're working, and I have a similar question with those weighting coefficients. You were kind of showing how you're trying to kind of put a rubber band on some weighting value to keep them from straying too far.
Yep.
But why do you think, why should we think that those weightings are well-behaved parameters, or are they mappable? Sort of how continuous are they, and how can you talk more about how to better think about what weightings ought to look like?
Yeah, right.
Because
So
I think you're kind of making some judgments that they should be fairly continuous functions spatially,
right.
or in the parameter space. But that sort of, I don't know if there's good reasons to believe that.
Yeah.
It makes sense intuitively, but I don't know if there's like a reason to believe it.
Yeah, like, so we're putting like we're making buckets, right? And we're saying that there is just one weight in each bucket. So we're not like spatially weighting these as we moved out from the center or anything like that, or and should we believe that? Like, I believe there is some more continuous behavior going on than what we're able to capture with this current model. There's a couple ways we could handle that. One is by making, smaller subgroups or doing them spatially, do that. There's also another attribute we could add to the model to, allow those to vary as a function of, distance. Right now, like how we judge kind of, do we believe these different completions uplifts in these different areas? Because we have discussions about them really. We part of our tool is, what some of the stuff that David has talked about is, we do put the coefficients up on a map and see if they make sense. We also, look at the residuals on a map to see if we're missing something somewhere. Yeah, so that's another layer. How do you make this thing more kind of, continuous? in
You know, another version of that might be, is it kind of a QC element to look at your weightings to see if they
yes,
are
yes, yeah,
smoothly varying? If it's a smooth continuous function, then you can feel like you've got it right. And if it's not, maybe that's a flag.
right, right. Um, that's kind of a part that we need to really look into and add. Um, you know, um, like if your reservoir, I guess, is changing, your geology is changing in a smooth function, that would be, I think, more critical. I think, you know, with our groups being so far apart, um, you know, the asset teams, the Montney team actually spends a lot of time, you know, talking about, you know, this particular weight in this particular group. Does it make sense? I don't know if I'm answering your question, um, but we just spend a lot of time QCing the attribute weights, right? Um, and you know, if there are these areas that kind of the Montney team knows perform differently, right now we're just sticking those in a bucket and saying calculate one weight for this area. I think we need
Maybe
to,
another question online with that, kind of as you deal with the different teams and the different areas, you have a lot of parameters, and as you're building this B3PO models to work in different areas, I presume that means that you have some features that go to quite low rankings um, in some areas and quite high rankings in others. And how do you, without having to teach everybody in the asset team all the intricacies of the model, how do you help make it a actionable tool for people, as opposed to everybody sort of second guessing it because it's not their core area of expertise wasn't sufficiently, they don't understand enough about what's going on.
right? So, hey, Cameron's kind of a expert in this. Did you want to like take that?
Yeah, yeah, I can take a stab at that. I think just to make sure we're clear here, so we don't have one B3PO model for all assets, not a one size fits all glove. So there are going to be different models with different variables for different assets, right? But within the asset, like the Montney in the subunit, in the different subunit and zones there, um, it's just a matter of education. It really is. It's just when we first started, just even linear models in general, there's all sorts of pushbacks. I'm sure every single person on this phone call has heard about 1,000 times. And it's really just kind of plotting it up in different ways and showing things and explaining why maybe something should be in there, but it's not because it's covariating with something else. And it's really just a matter of brute force, education to the end users, and pushing the points home as much as we can.
Yeah, and I think the other side of that too is, you know, we really rely on our you know, our engineers and our geologists in our different assets to kind of have kind of high graded the specific attributes that they want to use. Like they spend a lot of time kind of in the background running all kinds of models and, you know, convincing themselves of, you know, what's really driving our well performance and what attributes are making a difference, and is everything kind of performing like they think it should. And then we take kind of what they've identified and then we're kind of saying, okay, now that we've got your attributes, let's put these into some buckets and let's try this model out, right? Or this modeling algorithm out and uh, see if it works. But
Is
there's a lot.
putting the ownership on the asset team, like making them, like letting them know that this is their model, this is their tool. That's really where it helps.
Yeah.
With all the input from your geologists and engineers and sort of subject matter experts, have there been insights that were surprising, that sort of challenged and helped them improve their thinking about a factor they thought was really important that may have been either an ill-conceived parameter that needed some tweaking or not anywhere near as important as they thought, and the model kept pumping it down to like a zero weighting?
Yeah, that's a good question, right? Like, so yes, and I'm trying to think of a good example, but I can't. But yes, that has happened. I mean, throughout all our meetings and our working sessions, that has happened a number of times. Um, yeah, Cameron, what I don't know. Can you think of I it's happened, I just can't think of an example, really clear
Yeah,
example.
I mean, gosh, yeah, it happens so often and so
Yeah.
frequently. I think one that's kind of maybe a good example, it might not be a perfect example, is kind of the way we handle our, parent child and spacing and the interaction between them. That has evolved so many times from our initial attempts in, just classifying it as something as simple as distance away from a parent, and seeing where and how that falls short using the model, and going back and reclassifying and retweaking that parameter. I think that's probably the best example I have. I'm not sure if it's the right example or not, but yeah.
No, that's great. I think that's one of the opportunities with a lot of these tools is that using them as a pointer of where we can work harder or work smarter.
Absolutely. Yes.
Were your clusters of spatial areas, was that all done by subject matter experts, or did you use like a spatial clustering algorithm to split that out? Because one of my big questions with how funny Area 5 looked is I wonder if that should really be glommed onto its neighboring cluster compared to having 9 different areas, maybe 7 or 8 would
Yeah.
capture.
Right, right. Yeah, that's a really good point. Yeah, so for this we we've turned it over to our SMEs, right? Um, but uh, you know, and that's kind of an ongoing kind of part of the workflow and part of the debate and the discussion that we have is, what we've actually done, and what I haven't shown here is we probably have run a model where Area 5 was probably part of Area 3, right? And so we've ran all kinds of different, subunit groupings. Um, I've also done it algorithmically too, where, I just kind of, you know, identify these different kind of area clusters. I do it with a machine learning algorithm. Um, um, we defaulted to the subject matter experts because they felt good about their areas at the end of the day, right? And they felt like they've kind of mapped onto their knowledge of the play, right? And what they've seen, in their years kind of working that asset. So that's the way we went this time. But yeah, like I've got all kinds of ideas to do it, just do it algorithmically. But for me to get that model out the door, that would be a heavy lift.
Yeah, because if you just look at like Area 2 right here, like the difference is almost nothing because
Yeah,
there's like
right.
5x the data points, and I guess it's like a lead on is the reliance of kind of SMEs at every step gets buy-in, but how much do you lose in cycle time if you're dissecting this in 10 meetings
Yeah,
every model run? It just seems like compared to running it 10 times, if that makes sense.
yeah. So yeah, we spend a lot of time in discussions on this stuff, like just without a doubt. Um, and what we did is part of the app. Um, Maybe we come back and show more of our app at some point too. That'd be fun. But part of what Cameron is building and Natalie are building out is, so we do a run, we choose like this grouping structure, we choose different attributes, we run it. Then what we're doing now, or what Cameron's doing now, is writing all the stuff to a database. And then You know, so we go through all these meetings, we change a bunch of things. We've actually automated like, oh, here's all these different subgroupings I want to try. We just automate it and run it and save it. And then we come back into our app and we can also kind of see a summary of what models are doing better, when and where. Then we can kind of go in and ease some of that, some of the cycle time burden there, kind of by showing a summary and then being able to drill down, go grab a model and like look at it and like to dig into it and tear it apart.
When you talk about looking at more models like that, I think one of the really cool things that you've built in here is having, I think, kind of a series. You mentioned it at the end of naive models where they were missing a parameter. Can you talk more about the logic behind that and maybe how that, I think our tendency is to want to pump everything into an XGBoost or something and a neural network and let it try and model everything together. And it's a little counterintuitive that you might generate a more stable model, or maybe you don't. Maybe you can talk about model stability and kind of what the thinking is behind omitting parameters in some of these things as you average them together.
Yeah. So, how we, I guess, how we kind of convince ourselves that one of our features or one of our attributes is actually making a difference is we actually, put it into the model. We might have it in one model, have it out of another model. Then we'll just look at, difference in the, our predictive accuracy metrics. We're also looking at things like MAPE. We're looking at MAPE in our different areas and RMSE in our different areas. So that's one way, but one of the things that we're doing in the background is like when I'm showing these plots here. So these are, I don't know, Cameron's working on these right now. So what we actually do is take the slopes or the attribute weights or the coefficients from MLR, and we also take them from our B3PO model. And then we just run them through an equation to make a prediction by leaving, say, here we just left our propant per cluster out. And then we'll actually then map on the MLR lines of best fit and the B3PO lines of best fit. And we just want to make sure that they're, kind of projecting through the data from our different areas in the correct way. I don't know, that sounds like that answer might, Cameron, did you want to you have anything to add there? Did I cover it? I don't know.
No, I mean it's pretty good. I think that, yeah, what we're just trying to do is what do they call them? Not marginal model. Leverage plots, I think is what they call them. We try to use things like that. And once again, we've already transformed everything to where our effects should be linear. So it's pretty easy to look at these plots and see, okay, well, do the trends line up with and without? And does adding this variable actually make sense?
Yeah.
So is that's sort of helping you understand the relative importance of a parameter as you apply the model with it and without it, you get to better understand what's the delta delivered by incorporating that new parameter.
Yeah, and really with our B3PO process, the backbone of it is still the I don't want to say MBR, but it's still the more or less linear modeling process of we're going to go through that and really identify and determine the best variables. And then once we have those best variables, we're going to put them in this B3PO space. So the B3PO is not doing much variable selection. There is some going on, especially with these kind of marginal variables, but like the big ones are there. And the B3PO is not, the main purpose of it is not to whittle down a list of 1,000 variables and come up with a best model. Is to take our current best model and just really improve upon it.
Yeah, that's exactly right.
Excellent. Paul, do you want to chime in and ask some of your questions? I know you've been writing a bunch, and I don't know that we've really got to them right, but I think you might be able to ask them better. Maybe not. Well, I guess one last question I want to offer is I know that a lot of us are working on building our own models and our own systems to use at our own companies. You guys have built this, you've deployed it across a number of assets. Do you have any sort of parting words? I mean, we'd love to definitely have you guys back to talk about other aspects of this project, but do you have any parting words or guidance for people that, as you guys have gone through this and built this, there's a lot of challenges of getting people on board, of making things useful, of getting away from sexy models and going for things that just work. What have you guys learned that has either you would have done differently with hindsight, or that you might give as advice for people embarking on stuff like this?
Yeah. So this was really like a hard lesson for me, like, because I tried to roll this out internally in a number of different ways and find points over the last few years. And what I didn't spend a whole lot of time on was the education piece, or, kind of walking through kind of all the internal parts, which is kind of what I did today, right? So when I timeline my projects now, I always add in at least, if I'm going to spend X number of hours, actually building the model, I'll probably want to spend at least that amount of time and that amount of effort, into explaining it, helping people understand it. That was like a big pain point for me that, I was always under the gun from, I got a manager saying, well, where's your model? Where's your model? Where's your model? So, okay, I'll go ahead and, develop it and build it, right? And then it was like, well, we've got this cool model built, but nobody wants to use it, right? So really, that balance between model building, model explanation, and taking time to build those tools, building the graphs, all of that are really important.
Yeah, I'll completely 100% echo that. You cannot spend enough time making sure people are comfortable with the model. Dissect it
Yeah.
any way you possibly can. Choose as many different visuals as you possibly can, and just spend a lot of time making sure people are comfortable with it. No matter what kind of model it is, that's what you have to do.
And we found that across in different business, like different use cases, like different business areas, right? Doesn't mean even if I'm building something for, not even, but if I'm building something for, environmental health and safety, right? Or for finance or for whatever, right? Everybody wants to know, right? Like we're all making decisions based on these. And, if I'm in charge of making a, decision on, a particular design of a well, and I'm gonna like offload that and like trust a model to do it, like I I want to know what's going on, and I want to know the intricate details of that. So yeah, it's a lot of work, um, but
Well, I
I'm making
really
progress.
appreciate you guys walking through so much of it with us. We'll definitely have to have you guys back to talk about another aspect of it. There's been a lot, there's a lot of things that you've definitely clearly put a lot of work into this project, and there's a lot of other aspects of it that are fascinating.
Yeah, like we could talk about the whole Bayesian piece and all of that, which is really cool. And I really didn't touch on that today, but yeah, absolutely. You should see Cameron and Natalie's app is like really cool as well. So we'd be happy to come back and talk about other pieces at some point in time. If you would, if we get an invite back for sure. So
Of course, of course.
nice.
Well, I really appreciate you guys taking the time to put this together and to kind of help educate us a little bit about how you built this model and deployed it and got it working. And I think one of the most amazing pieces is just getting as many aspects of a company communicating through your model and using it. That's I think that's a challenge that almost everybody on the call experiences and deals with. So great work in just solving that problem to some degree.
Yeah, well, thank you. Really appreciate it.
Well, I really appreciate you guys giving this talk. I think we've got a recording of this, which we'll talk to you guys about afterwards and probably put up and share with people. And then